So now that we have talked about fairness, let us talk about how operating systems actually try to achieve such fairness. And the way that Linux, for example, do it is using a version of what is called a multi-level feedback queue. And a multi-level feedback queue is basically, sorry, designed to try to achieve everything at the same time, which basically means that it achieves nothing optimally. So it is designed basically to try to achieve the responsiveness of shortest job first, and that's basically by trying to run short tasks very quickly. It tries to achieve low overhead that FIFO has and minimize the time spent making scheduling decision. It tries to achieve starvation freedom, which is a property that you find in round robin, and it tries to achieve that fairness in the system and using the maximum fair share of the processor. And it tries to also have the idea of background tasks which should not interfere with user work. So background tasks such as memory cleanup. I mean, in theory, for example, the Java garbage collector should be one of these background tasks, but in practice it is not. So this is what it tries to achieve. And if you try to achieve everything, you probably do not achieve anything optimally. Basically, master of every jack of everything. That yeah, jack of everything, master of nothing. Of nothing. So an MFQ basically works like this. You have round robin queues, and these queues are have different priorities. So you have multiple queues. Within each one, you work with priorities, but in each queue, you work with round robin. And basically, you always schedule things from the highest priority queues first, followed by basically things from lower priority queues in sequence. But then, when doing that, you do not basically wait until you finish everything in the higher priority queue, but you rather use these priorities as weights, and that would basically means that you would try to run some tasks from the first queue, high priority queue, but also some tasks from the last priority queue. And for each priority queue, would basically have a different time slice for its round robin, because you're in round robin you have the quanta, you have the time slice for which your processor runs without any interruptions, and these would be different for different priority queues. So for short running jobs, for example, 10 milliseconds might suffice, and therefore you might have 10 milliseconds for your very highest priority queue, and that would be basically sufficient for IO intensive applications that just need the operating system very fast, but then would just release it after a few milliseconds. But then for longer priority queues, for higher priority queues, you would have a higher time slice. And that's the theory. We'll look at how Linux implements it in a very short while. So, in summary, to summarize how things are done in a unit processor, basically, you have trade-offs like everything. You have FIFO that minimizes overhead, but can result in very poor average response time. It also has some notion of fairness. I arrived first, so I finished first. But it also has some notion of unfairness because, well, you arrived first, but then you blocked the CPU for 10 hours. So uh, it's problematic. If tasks are equal in size, FIFO is optimal in terms of the average response time. And considering only the processor, SJF is generally optimal in terms of average response time. So just looking at the processor, shortest job first will give you almost always the best average response time, but one of the worst tail response times that you can think of. Therefore, you get very bad variance in response time. If tasks are variable in size, then round robin might help you a bit. It approximates an SJF, but then the best way to do it would be to use an MFQ, for example. If tasks are equal in size, then round robin will have very poor average response time because everything roughly finishes almost at the same time. So it's very bad in that sense. And then if you have tasks that intermix between processor and I/O, then you can benefit a lot by having SJF, but round robin might be a very bad idea because in that case you will have the application having to wait for 100 milliseconds basically doing nothing because it's round now. Well, it just needs 1 millisecond. Maximum fairness can improve response time for I/O bounded tasks. So if you implement some form of maximum fairness, this should basically improve your overall performance in terms of response time if you have I/O bounded tasks, and it avoids starvation because there will always be sort of a quota for. I mean, you will always try to equalize for different processors, for different processes. Sorry. Okay, and then the MFQ is a way to basically improve the overall system performance and try to basically be to be jack of everything but master of nothing basically. So for multiprocessor scheduling, I mean, all what we have been talking about is for uniprocessors. You have a single processor core and you run on that and you're trying to schedule things on that processor. But for multiprocessor scheduling, can you, for example, use a centralized MFQ with locking? And again, an MFQ is something that looks like this. So can you use an MFQ with locking? No. And the reason is that you will end up with contention for the schedulers using for the scheduler's pin lock. You'll have basically with an increased number of processes, MFQ will basically have contention when it comes to the scheduler spin lock because you will need all of them will need to call the scheduler basically. You will have cache slowdown. I mean, this is for a centralized MFQ, as I said. So you have a single scheduler queue and everybody's trying to access it. And there will be cache slowdowns because, well, you'll have the ready list data structure basically pinging between from one CPU to another, and also values pinging from one CPU to another. There will be very limited cache reuse, so caching will be hurt significantly. And then the solution is, of course, to have a pair processor data structure and use still MFQ, but then rebalance only when it makes sense. So you'll have an MFQ per processor basically, and as long as each MFQ has some jobs to run, some tasks to run, you will not try to rebalance. You will only try to trigger a rebalance when you end up in situations where one of the queues ends up really overloaded and the other one ends up lightly loaded or with no load at all.